start then by looking at the homework problem. Has anybody tried? Who hasn't tried? You have. No? You have. So you need to find an easy, pick one of those each, please. There might be some spare ones or whatever. What's it done? Oh no. It stopped working. Are there any witnesses that it was working 2 minutes ago or 5? Yeah. Is it working now? Excellent. It's not doing what I want it to do. Oh, whatever. Okay, so if we look at this problem, what are we going to do with it? Solve it, I know, but what does that involve? Is there anything that we call non-standard about this problem? Yeah?
Second equation, like the variables are greater than value they sum up to. Well, the x1 plus 2x2 will always be greater than 25 or equal to, which is not the same for max 90. Or is it the other way around?
This, yeah, that says greater than or equal to. So the constraint is greater than or equal to rather than less than or equal to. Okay. Were you saying anything about the solution?
No, I just remember that it uses 2 different slack variables.
Yes, that's right. Well, actually doesn't use any slack variable because the S is called a surplus variable if it's greater than or equal to. Or you can call it slack variable. It's not precise, but it's okay. It's usually called surplus variable, but it uses 2, and the other one is called an artificial variable. Okay, so the preparation for the two-stage, it's called the two-stage simplex procedure, right? And what we want to do is, well, the first constraint, okay, z minus 2x1 minus 3x2 equals 0. That's the same as it always is. But when we want the first constraint, then this is going to be, well, the first constraint is going to be we add a slack variable. Okay, that's normal, just as usual. The second constraint, however, we do x1 plus 2x2. Now, because it's greater than or equal to, this is more than 25, think. So we have to take away something positive to get 25. That's why we are subtracting this s2. That's called a surplus variable. And what we said was that in that case, we need to add an artificial variable. And so this is going to be 25. Now, during the first stage, what we're doing is we're trying to minimize an objective, which I call G, which is the sum of all the artificial variables. So in this case, there's only one artificial variable. And if we add it together with nothing else, then we get A2. Okay. Does that look familiar? So now I don't, well, so the fourth equation that I'm looking for which I've got space at the bottom, should express the same thing as G equals A2. Are you working? Seems to be working. 2 weeks ago, we should not be doing the recording. Okay, so I want an equation that expresses exactly this, but I want to not have A2 in it. Okay, because I want A2 to be the basic. So what I do is first I want to have, so this equation is the same as saying that G minus A2 equals 0 on our, to this equation, G minus A2 equals 0, I add the equation containing A2. And when I add them together, what I'm going to get is an equivalent system, but this can be replaced with a new one, but it won't have A2 in it. Okay? So when I do that, I get that G plus x1 plus 2x2 minus s2 equals 25. Is that right? I hope it is. Okay, so and I also still want I still want all these x's, s's, and a's to be non-negative. So just for the sake of completeness, I write x1, x2, s1, s2, and a2 greater than or equal to 0. And so when I've got this problem where I'm trying to minimize G over all possible solutions to this system with everything non-negative, I can use the simplex method. Okay, so what is the basis going to be? It's all the slack variables and all the artificial variables, but not the surplus variables. Okay, so the slack variables, there's only one. There's one artificial, and I have those objectives like this. And the rest should be easy. So value here is 10, here is 25, 0, 25. First row is 3 ones, 2 zeros, 1, 2, 0, minus 1, 1, minus 2, minus 3 zeros, and 1, 2, 0, minus 1, 0. Okay, so that's just coming from that system. What am I doing? Minimizing G. So when I'm minimizing G, what do I need to do, if anything? You're my hero, George, because otherwise I would ask questions and nobody would say anything. So, quite happy to
Raw
help.
values in the G function negative instead of positive. So instead of like being +1.
So you don't want 1 and 2. That's what you're saying. You don't like them.
No,
They need to go.
yeah.
So what do you suggest? A pivot step? Yes. Okay. Right. So that's it through. We talked about it. Tells us to take the most positive now for minimization problems. For maximization problems, it was negative. So that's this too. And then ratio test. Ratio test is always there. What is ratios? 10 divided by 1, 25 divided by 2. So it's 10 and 12 and a half. 10 is less than 12 and a half. Therefore, the pivot element is which one? Yeah, which one? The 1, 2, the -7 is this one. Okay. Because of this 2 being the largest element in the G row, and because these ratios being 10 and 25 divided by 2. So I'm taking the least ratio. Okay, that's the element. So when I do the pivot step, the basis changes to x2, a2, z, and g. The first row is divided by 1, and the rest I have to work out, and I get 5 minus 1, 0, minus 2, minus 1. And you were supposed to have done it at home. It shouldn't surprise you. But we're getting this. So now what? What's next? Is G optimal now? No? You knew it last time, man.
It seems to be.
It seems to be. Or you don't trust it.
No, still that's not great to be true. You do 0, but to get to that. So it's minimal as possible.
Can you see this? Everyone. Look at it again. I hope everybody knows what we're doing. Okay, so what we're doing is, once again, we're trying to solve this. So first of all, we're trying to find some x1, x2, and s1, s2, and get rid of the a2 here. And they should be all non-negative, so that we get a feasible solution to our LP. We're trying to find a feasible solution by solving first a different problem, in which we do have a feasible solution because we introduce some A2, which is bogus because we don't work. But it's useful to have it if we want to find a feasible solution. And then what we're trying to do is minimize A2. Hopefully, if A2 is minimized, then it will be 0. Because it can't be more than 0. We've got this condition that A2 can't be, sorry, it can't be less than 0. A2 can't be negative. So if it's the least possible, then we're hoping it's going to be 0. And if it is, then we can just remove it from everything, and we have a feasible solution. It's removed itself completely. That wasn't the idea. Now, what we've actually found out, by pivoting, is that the least possible value for G is 5. There is no way to make it 0. So there is no way to find a feasible solution. So there are absolutely no values that satisfy all these constraints. That's the conclusion that this is heading. So it was a bit of a, it was a bit unfair to give it to you as homework because we never did it. It was a challenge. So now you know what to do in these cases. Okay? So G has now been minimized. But the conclusion is so the original LP has no feasible solution whatsoever. I forgot. Okay, so I'll plot it later. You would see that the constraints just the half spaces don't have any common half planes don't have any common intersection. You plotted it. Okay. That's everybody's sleeping. So a linear programming problem which has no solution no feasible solution is called, what do you think it's called? Of course you have no idea. It's called infeasible. This is one of two cases when you get an LP problem and it has no optimal solution. It's the first one that we're really looking at. Okay. The second case we'll look at a bit later today, hopefully. So it's called infeasible. What? So of course it's quite easy to come up with an infeasible LP problem because you just draw things in the draw your constraint. No. And you can draw a constraint like this and say problem has to be on this side of this straight line. And then you draw another constraint, and you say the problem has to be on this side of this straight line. And you also say that x1 and x2 have to be negative. And so you see in this picture, there's absolutely nothing that, absolutely no intersection of these half planes. Because the two constraints that I've put there, they only intersect for negative values of x2. And if you want x2 to be non-negative, then you can't get anything. So this is a situation which I had in the which I had in the example, homework example. It looks a bit like this. Now, what does it mean in real life that? Come on. So in real life situations, however, you don't usually get infeasible LP problems when you have something in math. So in real life problems, infeasibility usually indicates something like this. For example, you were writing your constraints based on your making your model, and you did something wrong. So an error when writing the constraints. That can happen. Another thing that can happen is the model made too many assumptions, okay, or something, or too few. That's possible. Or it could happen that the managers are at fault. Usually blame the managers, right? I mean, it's like this everywhere. Except at universities. At universities, it's the other way around. So half of the students fail an exam, okay? Nobody blames the managers. Everybody comes and says, Jan, what have you done? They all failed decision maps. That's not happened. And, it's just an example. But even if the average mark is 67, they come and say, why is it not 69? Because the students are lazy, I say. But maybe I'm wrong. Okay, so what was I going to say? The managers made too strong requirements. So in that case, you can go back to the managers and say, well, what you want is not possible. And I have a mathematical proof that it's not possible. So change your mind. So if you have attempted the homework problem, you can mark yourself as attempted, otherwise mark yourself as and we'll move on. Are there any comments or questions about this? Okay, so I have a question. I have an important question. When do we use the two-stage simplex method? Not just the usual, but the one with the first stage with the G. When is it needed?
When was a slight variable?
That's one possible case, but why? I mean, why can't we just start with the usual thing? Okay, do you remember the geometry of the simplex method? We had a picture like this, and we said that we're starting in this corner down here. Yeah, and then we were moving, along edges of the feasible region. Is that right? Yeah. Now, what we wanted was that this corner here was a basic feasible solution. Okay? And feasible means that it satisfies all the constraints. And if the corner, which is all zeros for all decision variables, does not satisfy all the constraints, then we need the first stage. We need this two-stage simplex. Okay, that's the exact kind of answer to the question when or why. Both actually. We need the first stage. So the two-stage simplex is needed when the starting solution, starting basic solution of the usual simplex which is all the x's equal to 0, is not feasible. One such example was this problem, because if you put 0 and 0 into the second constraint, then it's not satisfied. Okay? So one example of such a situation is where you have a greater than or equal to in a constraint. Another example is this one, where you have, another example is this, but what you have is, okay, all the constraints are less than or equal to. So there's no problem there. But the problem is with the second constraint, because if you put zeros, you get 0 on the left, and you have a negative number on the right. Okay. So that's another situation where you can encounter the need for the first stage. What do you do in a problem with a problem like this? Anybody got a smart idea? Yeah.
Multiply the equation by -1.
How do you know?
So it changes the sign backwards. And then you treat it like the other example.
How do you know? You've seen it before.
No.
Did you come up with it by yourself?
It's
a good guess. It's a very good guess. Yes, that's what I was going to say as well. So yeah, so this is the right way for us at the moment, at least. In a situation like this, multiply the constraint the constraints, all of them with negative right-hand side by -1. Okay, when you do this, well, there's only one. This constraint becomes minus x1 plus x2 is greater than or equal to 2. And now you know what to do. Do we know what to do? Yes? Good. But where's the first homework problem that you have in your handout? Okay, easy enough? It's on this. Oh, yes. Something to read. Shouldn't say anything because people complain when I say things, but I wanted to give her thermodynamics. So that means that decision math is more interesting than thermodynamics. It's clear too. Oh, this one. No, that one. Keep forgetting what we're doing. Now, what we're doing is this. Look at this. When you put in all zeros for the x's, are the constraints all satisfied? Right. So this one's not. But now if you multiply it by -1, you don't get anything better, do you? So what happens is the recipe for this is that. Okay, so the first constraint, you can just add a slack variable. So the first constraint is x1 plus 2x2 plus s1 equals 4. Okay, there's no surprise there. The second constraint, you can't add a slack variable because there's no less than or equal to, and you can't add a surplus variable because there's no greater than or equal to. Or you can add an artificial variable. So what you're going to do is you do 2x1 plus 3x2 plus a2. I call it a2 because it goes with the second constraint, but you can call it anything you want, really. And this has to be equal to 5. And then, of course, you have the objective, so z minus x1 minus 3x2 is 0, and what do you get for g? Is it clear why? If not, you should ask. Okay, so G minus A2, this is all it's said. So the first row you get in the, sorry, the G row you get in the first tableau is going to have, going to be the sum of everything where you find any artificial variables. Set the artificial variable. If I add G minus A2 equals 0 with this, I get G. Okay. Something too boring. So what you do in this problem is in the first stage you do what you always do. Minimize G, and if you get to 0, you move on because you found a feasible solution. And if not, then you haven't found a feasible solution and there is none. Any questions? That's homework to finish it. Good. Have you got the book? Kenny's got the book. Does it have the summary of the two-stage method? Okay, so I won't read it. Just read it yourselves. Is there anybody who doesn't have the book and needs it? Okay, read the summary of the two-stage method, and then that's it for the first hour, I think. And then we can restart in 15 minutes or so again, and I'll bring you a book. Anybody else need the book? So we'll take a break now during which you should read the summary. And then if you have any questions about anything in that summary, we'll discuss it. If not, then we'll move on to more problems. Okay? Even fewer people than before. So the thing is, we should probably not care about people turning up. We should care about them. For example, I feel the same, so it's not fair that you are expecting me to entertain. I'm expecting you lot to entertain me. It says one viewer, so someone's watching now. Oh, it's live. No, I shouldn't have said that. Next time, nobody's going to turn up. Everybody will be. Everyone's going to be on YouTube. Oh, he's asking questions now. So maybe we should start the chat. Like I'm just going to be on the chat, and you can ask questions. No, that's silly. It's live, but it has the disadvantage that if something goes wrong on Google, on YouTube, then it disappears, like it did 2 weeks. It seemed like it was live, and everything was okay, and then when I looked at it, there was a 2-hour video, and it was all black all the way and no sound at all. I don't know what happened. Now, if you're watching now and everything's okay, can you nod? They're not there. Yeah, I don't know how to do that. Okay, well, I'm nodding at that computer, but is anybody still missing who wants to come back? Do you know of anyone? Is someone there? So we'll wait for a second. Does anybody do their A-levels in chemistry? Do you understand it? What is it? I just found it. It's not mine. Don't blame me. Okay. So let's go on then. Any questions about the two-stage simplex method? No? Everything clear then? Just to emphasize the key point, yeah? When it's used when putting everything, all the x's to 0 does not satisfy all the constraints. Okay? That's the situation where you want to use it. And that can differ things like greater than or equal to constraints, or equal constraints, or negative right-hand side, or that's appropriate. Okay? And then you need every constraint which is not satisfied needs an artificial variable. So only those constraints that are not satisfied need artificial variables. The other ones are fine. You just add a slack variable, a surplus variable, whatever, and that's fine. But those that are not satisfied by default zeros, they need artificial variables. Now, there you minimize G, which is the sum of all the artificials, and yes, that's it. And when you find the minimum is 0, you're happy. And when you find the minimum is non-zero, then, well, in a school question, you're even happier because that's where you can stop and you don't have to do the second stage. But, in a practical problem, you know, you started without them. So, do you have any questions? So you can see, because of the book, that the next topic is unconstrained variables. What is an unconstrained variable? These are the decision variables that we don't want necessarily to be greater than or equal to 0. Okay, so when in the examples we've seen, we usually wanted all the decision variables to be greater than or equal to 0, but sometimes you don't mind. So there are practical examples of problems like this. One of them that we will see much later is comes from game theory. Okay, so when you've got a zero-sum game, you can solve it using linear programming, and there are decision variables that don't have to be non-negative. So we'll see an example of that. What does one do? How do you solve it? Okay, so the basic complete, not complete, but the essential condition for the simplex method to work is that it wants all the variables that are in the tableau, or all of them, to be constrained to be non-negative. Because if they're not, then everything breaks down. Okay, well, everything. The main thing that will break down is that the optimality criterion, which is for maximization problems, there are no negative entries in the objective mode. If you have variables that can be negative as well, and this doesn't work anymore. So the simplex method really relies heavily on that, on having everything greater than or equal to 0. So when you get a problem like this one, where it only says x2 greater than or equal to 0, and x1 can be negative, that's a problem. So you can't just solve it as the usual simplex method. What you can do, however, is, so the recipe for this is you replace the variable which, or all the variables really, which don't has to be non-negative with two new variables. I call them x1 plus and x1 minus. Okay. The idea is that if x1 happens to be positive in the optimal solution or in some feasible solution, then well, this x1 plus is going to have the same value as x1. Okay. And if x1 is negative, then this x1 minus is going to have the opposite value. So for example, if x1 is -7, then x1 minus is going to be 7. Like this, you can have both of these two negative and solve the problem, and then go back to x1. So more precisely, we want x1 to be x1 plus minus x1 minus. Like this. Okay. So it can happen that they're both non-zero, but it won't happen. In a basic, in the optimum solution, it's not going to happen because of the properties of the simplex. I don't want to go into that. But even if it happens, it doesn't really matter too much. So then the new LP would be to maximize. We need to maximize. Well, 3x1, so that means 3x1 plus minus 3x1 minus, okay, plus 5x2. x2 is non-negative, so we don't do anything with it. Subject to the constraints. So what's the first constraint? That's easy. x1 plus minus x1 minus is less than or equal to 4. 2x2 is less than or equal to 12. And 3. What am I doing? Yes, correct. Sorry. 3x1 plus minus 3x1 minus plus 2x2 is less than or equal to 2x2 is less than or equal to 18. And now require all these new variables to be non-negative. Okay, that's simple. Make sense? Good. Have you solved it yet? Probably easy, but if not, then it's something like a homework 3. Okay. Any questions? Who wants to go home? No? One more thing. Last thing is this. Okay, we've got this problem. So look at it. Oh, you can't see it properly because of this bloody thing. Okay, now you can see it. The problem because my slides don't assume that there's going to be a wide angle projector. But it isn't. So, okay, so is there anything wrong with this problem? Let's try. For example, do we need the first aid? All zeros are feasible. Everything's supposed to be negative, so there doesn't seem to be anything wrong with it. The only thing that happens to be wrong with it is that. Okay. I'm starting to be very lazy. I'll just show you. Okay, this is the. Okay, we're trying to maximize. We're at the first tableau. This is supposed to be first pivot. Why? Well, because 2 is the most negative. And we need a positive pivot element. Never do any pivoting, negative or 0 pivot element. So the only positive is this one. So we do the pivot, and we get this tableau. Okay. Is this finished? No. Why not? Right, yeah. This is negative value here. Can you make another pivot? No, because there's nothing positive. Any idea? Okay, what's happening is remember this picture? When we're doing our chest set pivoting. And then for example, we're doing the second pivot step. So we're here, the basis is x2, x1, x3. We want to pivot. The ratio test decides that we should stop at this point, meaning that S3 should leave the basis. If we're stopping where okay. Then one of the larger ratios would be stopping here, and the largest ratio is stopping here with this line. Sex the okay. Now the thing is, if in that column the entry is negative, that means that the line that we're going on intersects that particular constraint on the other side. Think of it as the least ratio is here, the second least ratio is there, the largest ratio is at the end. And all negative ratios are on the other side. And if everything is negative, that means that we can go along this line and we never encounter another constraint. Okay, that makes sense. I'll draw an example. So, should have drawn the example of that. But you can, so when I have something like this is x1, this is x2. Okay, let's say one constraint, this is another constraint. And the feasible region is everything okay. And I'm trying to maximize some function that is going up and to the right. And for example, in the first pivot step, I move over here. And then in the second pivot, I'm starting to go here. And I go and go and go, and I never meet any other constraint, and I can go to infinity, and that's it. So if you're going that way, you can keep increasing your objective as much as you want, and there's nothing stopping you. And a thing like this is called an unbounded problem. It's a maximization problem. You can increase your objective without any bound. The minimization versus you can decrease it without any bound, and that's called a minimization problem. And the way you find that is that exactly what we had here, which was that no side exactly when there are no positive numbers in this column. Okay, I'll just write it down if this thing. Come on, okay. So, and the second tableau. There is a negative entry in the objective row, but no positive entry above it. So no pivot is possible. And we call this an unbounded problem. So the objective can be made arbitrarily large, and there is no optimal solution. Anything else that I need to add? No questions? Okay. The homework problems are clear. Each of them is an example of what we did here. So negative right-hand sides, equality constraint, unbounded variables just wants you to finish the thing so you can get a bit of a feel for what these things are like. Good time. Next week, I'll have the, what is it, 1 o'clock, the early afternoon lecture. So everyone's happier when they have a 1 hour lecture, I'm told. What I was going to do is we'll have a look at the homework problems, of course, and then there is, at the end of chapter 2 in the book, there is an example exam question. So it would probably be too much to expect people to look at it before coming to the lecture, but what we're going to do is solve it there and go through it so you get an idea of what compulsory exam question is like. Oh, and I also have to bring prizes for those who have done the most homework. So that would be a bit good Christmas lesson. That is everything. Anything else that you might want to say? All right, then. Thanks for coming and staying. Enjoy the rest of your week. We'll see you on Thursday or Friday or next week.